In section 7, there is one big idea that we need to walk away with. So one big idea about infinite series is that it is possible to add up an infinite number of terms in a series and get a finite value. So it would be perfectly reasonable to think that that's not possible. If I'm adding up infinitely many numbers, it seems like that sum should increase and be infinitely large. But it turns out that if the terms of a series decrease to 0 fast enough, that it is possible for an infinite series to have a finite value. So for clarity, many series don't have terms that decrease at all. If the terms of our series increase, that is going to continually, like our sum is going to get bigger and bigger and bigger. But it is possible for our series to converge to a finite value. So if we look at this series, 1/2 to the power of n, so our first term, right, would be like 1/2 to the power of 1, because we're starting at n equals 1. We'd add to that 1/2 to the power of 2, that's 1/4. 1/2 to the power of 3, that's 1/8. And we're going to add this forever. We're going to keep adding, like my next term I'm going to add will be 1/2 to the power of 4. So it seems implausible at first that this sum could actually converge to a particular value. It seems like the sum would get bigger and bigger the more numbers you add. But for illustration, let's look at the square to the side. So geometrically, this is a square with a side length of 1 by 1. And so if I cut my square in half, I could think of this area, I could use like this as an area model to represent the first term in my series. So with the half that remains, if we cut that in half, we now have 1/4. So like that's my next term I'm going to add up. With the half that remains, I could cut that in half, and I have 1/8. Then when I cut that in half, I'll have a 16th, and I could keep going forever and ever and ever and ever. When I cut a 16th in half, the 16th that's left, I'll have a 32nd. Then I could cut that in half, have 1/64, cut that in half, 1/128, and I can keep cutting these little pieces in half forever. But if I look at the sum of this series as the area of all these like tiles that model the different terms in the series, I could see that they add up to 1. So a series, or the sum of the terms of a series, can have a finite value. So the series can have a finite value, meaning that our series converges to a finite value. But the question is, when does this happen? When does our infinite series approach 0 fast enough? And how fast is fast enough? So that's our big idea. If the value of an infinite series is infinite, we say the series diverges. So if I'm adding up all of these terms forever and ever and ever, so it's an infinite series, and I keep getting a number that grows larger and larger and larger, that means my series is infinite, and that series diverges. However, if the value of an infinite series approaches a finite value, we might call it L, we could say that that series converges to L. So let's consider the harmonic series, because when we ask the question, how fast does a series have to approach 0? The boundary that we're going to consider is the harmonic series. All right, so the harmonic series is the series 1/n, starting at n equals 1 as n goes to infinity. So if we consider the sum of 1/n as n goes to infinity, we've got 1, then 1 plus 2, or sorry, then plus 1/2, excuse me, I read that wrong, plus 1/3, plus 1/4, plus 1/5. And this will go on forever as our denominator just continues to be n. And so if we take a look at figure 1 below, This is the harmonic series. And it turns out that the harmonic series itself diverges. So the harmonic series diverges. It does not approach, or rather its terms do not approach 0 fast enough. So like my first term is 1, my next term is 1/2, then a third, then a fourth. Those numbers are getting smaller and smaller. Each term is approaching 0, but it's not happening fast enough. But we consider our harmonic series kind of like our boundary case, because any series whose terms approach 0 faster than the harmonic series will converge. Any series whose terms approach 0 slower or don't approach 0 at all, but if the terms approach 0 more slowly than the harmonic series, that will diverge. So in figure 2, just here's an example. If we look at this series, 1 over n squared, I could see that like the harmonic series, my first term is 1. My next term is 1/4. In the harmonic series, my next term would be 1/2. My next term is 1/9 of the series 1 over n squared. But in the harmonic series, the next term would be 1/3. So as I look at each like subsequent term, I could see that 1/9 is a lot closer to 0 than 1/3 is, even though both of these series started at the number 1. If we look at this on the graph, the graph that is in black, that is the harmonic series. Well, on your paper, they're both in black. On my screen, one is red. So if I look at the red graph, the figure beneath the harmonic series, that is this series. So I could see, even though we start at 1, that immediately the values or the terms in this series are getting closer and closer and closer to 0 faster. So this series diverges. And for right now, I said diverges. I'm sorry, this series converges. So this series has a sum, and the sum is a value. And so for right now, it's not really important what that value is, but it's important that we know we could add up every term in the series 1 over n squared, and we're actually going to get a value. And this is going to be a really important idea for us later on. So if we look at one more example, again, the series in black here is the harmonic series. So it starts off on top, but we can see it on bottom over here. And in the second example, the series in red that we're looking at, that is the series. We have to start at n equals 2 because of our input here. That is the series 1 over the natural log of n cubed. So when I consider that series, even though initially it starts at a lower value than the harmonic series, I can tell after a couple of terms, the series kind of levels out. It is not, it's approaching 0. Each term is approaching 0, but it is not approaching 0 as rapidly as the harmonic series. So I can see that is approaching 0 more rapidly. So remember, we're going to think of the harmonic series as the boundary for when a series converges versus diverges. So this series diverges. The terms in the series do not get close to 0 fast enough for it to converge and have an actual value. So again, right now, knowing the value of a convergent series is not our primary objective. It's just understanding that a series can converge, an infinite series.